Hello everyone, I welcome you all to this course on Applied Thermal Engineering. This is our first module, IC Engines, Internal Combustion Engines. I'm V. Praveena, Assistant Professor, Department of Mechanical Engineering, SRMIST. So the contents of this course are classification of IC engines, basic operations of engines, actual PV diagram of 4-stroke Otto cycle and 4-stroke diesel cycle, the theoretical PV diagram, engine performance parameters, measurements of fuel and air consumption, brake power measurement and in-cylinder pressure, and finally the heat balance sheet. So starting with the introduction of engines, engine is a device that converts energy from one form to another. So for example, heat engines, electric motors. Here we are going to discuss about heat engines, which is a device that converts heat energy into mechanical energy. The heat engine finds wide applications in automobiles, transport and industries. We are going to see the classification. Classification is done on different categories. The first category and the foremost would be, the main category would be external combustion and internal combustion engines. In case of external combustion engines, combustion takes place outside the control volume. Example, steam engines. Whereas in IC engine, combustion takes place inside the control volume. Example, petrol engine and diesel engine. Based on the type of fuel used, we can classify the engines either as petrol engine or diesel engine. Based on the method of ignition, it can be a spark ignition or a compression ignition engine. In case of spark ignition engines, we use a spark injector to ignite the fuel, whereas in compression ignition, the compressed air helps to initiate combustion of the injected fuel. Number of strokes can be 2-stroke or 4-stroke. And coming to the number of cylinders, we have single cylinder or multi-cylinder. Based on speed of the engine, we have low speed engine, medium speed and high speed engine. When we say medium speed, it is restricted to 1500 RPM. According to the cooling system, the engine can be either an air-cooled one or a water-cooled one. So here we can see the inline engine, V engines and flat engine type configuration. The first figure, the animated figure, shows you that there are 4 cylinders which are arranged on the same line. The second type, that is a V engine, has got cylinders arranged in 2 axes which are inclined to each other, forming a V shape. And the last category, we can see the engines are arranged exactly opposite to each other, that is 180 degrees apart. There are many components in an IC engine. Each component plays its own important role. So to start with, we have the engine case, which covers the entire category of components. We have the piston that moves inside the cylinder from TDC to BDC, and there is a connecting rod which connects the piston to the crankshaft. There are inlet valves and exhaust valves. The inlet valve helps to supply the air or the air-fuel mixture in case of petrol engine into the cylinder, and the exhaust valves helps to deliver the exhaust gases to the atmosphere. The inlet valves and exhaust valve open and close with the help of a cam mechanism. They are driven in connection with a rocker arm, valve spring and a push rod. The power is being delivered at the crankshaft. The crankcase, it encloses the bottom portion of the engine. The crankshaft is connected to the flywheel. So this figure shows the 4-stroke petrol engine operation. The first stroke being the intake stroke. Here we have the inlet valve opened. Air plus fuel rushes into the intake valve, and the piston moves from TDC to BDC. In the second stroke, that is called the compression stroke, both valves remain in closed position. The piston moves from BDC to TDC, and we see that the air-fuel mixture is at high pressure. And at the end of this stroke, a spark is being ignited by the spark plug. In the third stroke, that is a power stroke, the fuel-air mixture burns, and the combustion gases are at very high pressure and temperature, and this helps to push the piston down, and therefore we see that there is expansion of combustion gases, and this continues until the piston reaches the BDC. In the exhaust stroke, we find that the exhaust valve opens and the burnt gases exits out through the exhaust manifold to the atmosphere. So these are the 4 stroke and functions in a petrol engine. In diesel engine also we have the similar 4 strokes, whereas here the spark plug is replaced by a fuel injector, and the fuel and the medium that gets compressed is only air. In the third stroke, as the fuel is being injected through the fuel injector, we find that combustion occurs, and that is shown by the red zone on the third figure. So this figure will clearly explain the difference between the actual PV diagram and the theoretical PV diagram of a 4-stroke Otto cycle. We notice that there are intake strokes, exhaust, compression, expansion and ignition which are shown in the actual PV diagram, whereas in the theoretical PV diagram, the compression and expansion process are considered to be isentropic. The intake process and the exhaust process are not shown. And also the point to be noted is heat is added at constant volume in case of Otto cycle. In this figure we can see the PV diagram, that is actual and theoretical, for a diesel cycle. So here the intake and suction stroke are shown in the actual PV diagram, and we can see that the heat is being added continuously from point 2 to 3, and then there is an expansion process from 3 to 4, and finally there is an exhaust. Whereas in the case of theoretical PV diagram, there is no intake and suction process shown, whereas heat is being added at constant pressure and heat is rejected at constant volume. The expansion and compression are here also assumed to be isentropic. There are many parameters to evaluate the engine performance. To begin with, the first one is indicated power, then brake power, frictional power, torque, mean effective pressure, specific fuel consumption, thermal efficiency, mechanical efficiency, volumetric efficiency, air standard efficiency. So we'll see one by one. The first one is indicated power. The power developed by the combustion of fuel in the combustion chamber is called indicated power. The chemical energy of the fuel is converted into heat energy, and that is denoted as the IP. It can be calculated from the mean effective pressure. So in this formula we can see N, P, M, L, A and K by 60. N represents the number of cylinder, PM is the mean effective pressure, it is the average pressure of all cylinders, and A is the area, L is the stroke length, N is the rotational speed, and K is a constant which takes a value of 1 for a 2-stroke engine and half for a 4-stroke engine. This is because for every 1 revolution of crankshaft, power is being produced in a 2-stroke engine, whereas for every 2 revolutions, only in one revolution power is being produced in case of 4-stroke. So hence the value of K ranges between 1 and half. And this 1000 is for conversion to kilowatt. Here we can see the brake power. So this is the power that is available at the shaft. This is developed by the engine at the output shaft. When the torque is known to you, 2 pi nt by 60 will give the brake power in terms of kilowatt. Brake power can be measured based on the type of dynamometer used. We normally use eddy current dynamometer or hydraulic dynamometer or electrical dynamometer, sometimes brake type dynamometer. In the brake drum dynamometer, the diameter of the drum will be mentioned. So that is this parameter d suffix d. If the rope diameter is also given, then that has to be added along with the drum diameter. So W is the net load and S is the spring balance reading. So this gives the BP in case of brake type dynamometer. The frictional power can be calculated by the difference between indicated power and brake power. It is expressed in kilowatt. Next is a specific fuel consumption. We can define this term as a mass of fuel consumed per kg per kilowatt hour. If the specific fuel consumption is calculated based on indicated power, then it is called as indicated specific fuel consumption. If specific fuel consumption is based on brake power, then we call it as brake specific fuel consumption. The mean effective pressure, it's a hypothetical pressure that is acting on the piston and is responsible for the power produced. It is normally given in terms of bar, and this can also be stated in terms of IP. If it is in terms of IP, then it is indicated mean effective pressure, else it is BMEP, that is brake mean effective pressure. The mechanical efficiency is calculated as a ratio between BP and IP. Indicated thermal efficiency is the ratio between indicated power and heat supplied. When we say heat supplied, it's a mass of the fuel into its calorific value. So this is the heat input to the engine, whereas the output from the engine is IP. But after the losses are considered, only the brake power is being available at the engine shaft. So the brake thermal efficiency is BP by heat input. Heat input remains the same in both the expressions. So the air standard efficiency, this is the ideal efficiency when air is used as a working medium. And there's also one more assumption that the compression and expansion are isentropic. So here we see that the Air efficiency for petrol engine is 1 minus 1 by R to the power gamma minus 1, where R represents the compression ratio. In case of diesel engine, we have one more term called as the cutoff ratio. So the compression ratio and cutoff ratio decides the efficiency in case of diesel engine. The next is the relative efficiency. So this term is very important because it gives the overall performance of the engine. So indicated thermal efficiency to air standard efficiency is the relative efficiency. Volumetric efficiency is a ratio of volume of air that is admitted during the suction stroke to the swept volume of the cylinder. The next is a heat balance sheet. Okay. The heat balance sheet gives a complete record of the heat that is injected during a certain time by an IC engine and how this heat is being dissipated away. Normally the heat input to the engine is only the fuel supply into its calorific value, that is mass of fuel into calorific value. Part of this heat is being carried away as indicated work. The remaining is being carried away by cooling water, some by exhaust gases, and the remaining are cannot be tabulated experimentally. So we call that as unaccounted losses. So as discussed earlier, the indicated power is calculated using the mean effective pressure. So this will be the useful work. This is the heat carried away by cooling water. The engine casing is allowed to cool down by using cool water. So this water, as it circulates through the cylinder, will have a tendency to gain heat and then it comes out. So we see that the water enters the casing at atmospheric temperature, whereas it comes out at slightly higher temperature. So this difference is your delta Tc, and mCp delta T will give you the heat which is carried away by cooling water, where Cp is the specific heat of water. Next is exhaust gas. Some amount of heat is carried away by exhaust gas to the atmosphere. So to calculate this quantum of heat, we can use two methods. One is implementation of a calorimeter, the other one is without a calorimeter. Now we'll see the method without calorimeter. When we don't have a calorimeter, we can calculate the mass of exhaust gases as a summation of mass of air with mass of fuel. And the delta difference, that is the temperature difference between TEG1 and TEG2 is, EG1 will be the atmospheric temperature, room temperature, whereas EG2 will be the exhaust gas temperature at the exit. The second method is with calorimeter. When we are using a calorimeter, the water that is passing through the calorimeter will have a heat exchange between the exhaust gases, so that the heat lost by the exhaust gas will be equal to heat gained by the water in the calorimeter. So we can use the mCp delta T, calculate the heat carried away by exhaust gas with calorimeter. There are always some losses which cannot be found out experimentally. To obtain this loss, we normally calculate, we sum up the useful work, heat carried away by cooling water and by exhaust gas, and subtract the net quantum from the heat input. So that gives away the unaccounted loss. So these are all the ways to understand the performance, the parameters affecting the engine working. So next we are going to see what are all the methods that are used to find out the air consumption and fuel consumption. So here the air consumption method, we normally stick to air box method. It is very difficult to find out the actual air inlet because of the pulsating nature of the engine. The engine is cyclic in nature and also air is compressible, so there are practical difficulties. So we are sticking to this method. Here we can see an air box and there is an orifice on one side, whereas on the other side it's connected to a manometer. Air is passed to the large tank whose volume is 500 to 600 times of the swept volume of the engine through the orifice plate, whose diameter and coefficient of discharge are known. Then air is passed to the engine. Outside air is assumed to flow continuously through the orifice with constant velocity into large tank. The velocity of air depends on the pressure difference between tank and atmosphere. Pressure difference is measured with the U-tube manometer, where one limb is always open to the atmosphere. So here the difference in manometric head is represented by the small case h, and density of water and density of air are known to us. So with this, the variation in head of air can be calculated, which is represented by h. The quantity of air passing through the orifice is given as CD A into root of 2GH, where CD is the coefficient of discharge for the orifice and that is taken as 0.6. Next is to measure the brake power. There are two types of dynamometers which are used to measure the brake power. One is absorption type and other one is a transmission type. The absorption type dynamometers, they are actually performing in such a way that some portion of power output is absorbed by them when they are coupled to the engine. Examples of them are eddy current dynamometer, rope brake and hydraulic dynamometer. Whereas in transmission type dynamometer, power is transmitted to the load coupled to the engine after it is indicated on some type of scale. You also call them as torque meters. So here is a picture of a rope brake dynamometer. We can see the brake wheel drum and there is a rope connected to it. One end of the rope has got a spring balance, another one has got the dead load. So as we saw the formula in the earlier slide, W minus S pi d n by 60 will help you to calculate the brake power. In cylinder pressure, as the piston keeps moving inside the cylinder, the pressure is different at every single movement of the piston, at every location. Say with respect to every crank angle, when the rotation is from 0 to 360, at every single crank angle the pressure and volume are different. So this cylinder pressure has been calculated using a piezoelectric pressure transducer. So here we can see the a schematic of the transducer connected to the cylinder. So here this is the pressure transducer which is connected to the engine. When the variation is being sensed, it is being sent to the charge amplifier and then to the system that it is being analyzed, charge amplifier and then the analyzer, and we get the crank angle data on the PC. Pressure measuring system, it consists of mainly the pressure pickup, amplifying device, a time-based recording device and a display unit. So with this, we'll wind up this module. Thanks for watching.